A very good morning to the course of micro engineering and welcome back to the course. In today's lecture, we are going to go ahead and see the different types of passive microwave junction based devices. If you recall, in our last lecture, we have started studying the different types of passive devices which are constructed by making use of rectangular waveguide section. So last time, if you could remember, we have gone through the different types of devices like frequency meters, waveguide bends, waveguide twist, and we have seen how the phase shifter is going to operate. We understood the working principle of attenuator. So in this particular lecture, we will go ahead and we will go into the details of other different types of passive microwave junction based devices. So here we are going to see a different variety of waveguide junction based devices which are normally passive in the operation. So the term passive waveguide based junction devices, that means these devices do not have capability to generate the signal, right? So that's why they are known as a passive devices, right? So first of all, let us go to the introduction to these junction devices. Normally, the design and integration of any communication system that requires several devices and different components. The junction based devices that will consist of different T's that we will see, directional coupler, isolators and circulators, etc. So today's lecture we will devote to this passive microwave junction based devices. So the agenda today is to study of passive microwave junction based devices. Okay, so first of all, what they consist of? It consists of, they are fabricated using waveguide section. So this is the important property of passive microwave junction based devices. Second, they are called as a passive as they do not have ability to generate the microwave signal. So that's why this is the reason they are called as a passive. Okay. In the next lecture, we are going to see the different types of microwave signal generators. So those normally we call it as active devices. So the devices today we are going to see, they are all passive devices as they do not have any ability to generate the microwave signal, right? So the examples of passive examples that we study. So the first example is we are going to see the different types of T's. We'll come to this particular part, what do we mean by T. Then we can study the directional couplers. Okay. Then we are going to see the isolators. Okay, and then circulators. One by one, we will go through all these different types of passive devices. Those are junction based and which are constructed by making use of waveguide sections. Okay, and circulators, isolators, and we have gyrators and power dividers. Okay, so these are the typical examples of passive microwave junction based devices. Okay, so one by one we will go through each of these different type of passive microwave junction based devices and we will see their construction, for what purpose they are being used and how they are typically going to operate. In some of the passive microwave devices which I listed over here, we are also going to derive the scattering parameter matrix for those devices. Okay, so one by one we will go through study of these different types of devices, right? Now, in the microwave system, which involves several different components, it necessarily requires one or other kind of a modeling of the parameter for their analysis purpose and for design purpose. Okay, so a microwave system can be constructed using these different passive type of a devices. Okay, so when a microwave system is constructed, we want to analyze that system. So in order to analyze and model the parameters, we require certain specific parameters. Okay, so and we already know that at a high frequency, the best choice to make use of analysis is by making use of a scattering parameters. Okay, so scattering parameters or the S parameters are the best choice because they are compatible in order to get operated at a high frequency. And normally a microwave system which consists of these different passive devices can be conveniently analyzed using scattering parameter. Well, so whichever this particular device that we are going to analyze, that particular device in terms of a scattering parameter, right? So the microwave junctions, so why these devices are called junction? Because they are constructed by making use of pieces of transmission line. As it is seen over here in this particular statement, it is mentioned that they are fabricated using the pieces of waveguides, normally a rectangular waveguide. Okay, so the microwave junctions are one of the important class of the device that are used in a communication system for variety of different things. For example, splitting of the microwave signal, combining of the microwave signal, sampling of the microwave signal, all these different processes can be accomplished using these passive microwave junction based devices. Okay, so these devices can have any number of ports, but normally 3 to 4 ports are quite observed phenomena in these devices. Okay, so there is no restriction that these microwave passive devices are going to have how many number of ports. Okay, so there is no such as limitation imposed on it, but normally when we make use of those devices in the microwave system, they generally consist of 3 to 4 different ports, right? And it is a common phenomena. So they can have any number of ports, but mostly 3 to 4 ports are very quiet and very common. Some of the passive microwave devices such as isolators, circulator, they are going to make use of non-reciprocal magnetic materials known as a ferrites. So we will come to this particular part later on. And ferrite are special type of a magnetic material which are used in the construction of typical passive devices like circulators and isolator. Okay, and these are known as a non-reciprocal devices. Non-reciprocal devices means the port configuration that we cannot alter. If you recall the study of properties of a scattering matrix, from that we discussed the property of reciprocity, and we gave that time the example of a best reciprocal device, that is the antenna. So the antenna can be configured as a receiving antenna as well as transmit antenna. So the port configurability for a given device, if it is interchangeable, then that particular device we say that it is following the property of reciprocity. On the other hand, the ferrite material, which are a special type of a magnetic material which are constructed in the design of isolator and circulator, these are non-reciprocal devices. That means whatever circulators and isolator we are going to design, whatever number of ports that they are going to have, their functionality of these ports cannot be interchanged, right? So this thing we will come across when we study the ferrite based devices such as isolator and circulator. Okay, the reciprocal passive devices, all other remaining devices are more or less reciprocal in nature, and these devices are different T's directional couplers. Okay, so the microwave junctions are the devices used at a microwave frequencies in order to split, in order to combine the microwave power. So these are passive devices and they can be made with the sections of a coaxial cable or by making use of pieces of the transmission line. Now make sure that here construction of these devices can be done using the pieces of waveguide, or they can also be constructed using segments of coaxial cable, right? So there are two ways to construct these passive junction based devices. Either you can make use of a waveguide or you can make use of a coaxial cable, right? What is the port? Now the term port refers to an opening structure to which either we can connect a source or a load. So a port is basically an inlet or it could be an outlet of a particular junction based devices. Okay, so the arms are the pieces of a transmission line or the waveguides with which the junction device is fabricated. Okay, so the junction region is very common space and where all the arms of the device are going to meet each other. So when we see a typical construction of passive junction based devices, these terms will be clear to you, right? So the junction region is a common space. So depending upon the manner in which the port is located in the overall structure of the junction device, it can be matched or it can be mismatched to one of the junction region. On the similar basis, for a two-port device, depending upon the location of the ports in the junction region, these ports can be isolated or they can be connected with each other also. So a port is said to be perfectly matched. So if you recall again from the properties of a scattering matrix, a property of matching condition, what type we define that time? Normally, a port of a particular given network is said to be perfectly matched to the given junction if nothing out of the power incident at the port is reflected back. Okay, so if this is a particular case, then at that time we say that the port is perfectly matched. Okay, and if the device consists of such a two ports, then these two ports are said to be perfectly matched if they follow this particular property. These two ports can also be isolated from each other if nothing out of the power incident at any one port appears at the other port. Okay, so if the power is incident at any one particular port and it doesn't come or it doesn't get contributed to any other remaining port, then at that particular time these ports are said to be isolated from each other. Okay, so these are the important properties that we call it as a condition of matching of the ports, then condition of isolating of the ports from each other. So these are very frequently we are going to make use when we are going to study these different types of devices, right? So in order to analyze and understand the functioning of these devices, it is necessary to understand how the scattering parameters are operated. Okay, so first of all we will go ahead and we will see 3-port junctions and thereafterwards we will see the 4-port junctions. Now please remember, entire passive microwave junction based devices can be classified into 3-port junction and 4-port junctions. So first of all we will study all those passive junction based devices which consist of a 3-port junction. Okay, so a common example of 3-port junctions are E plane T and H plane T. So here I will start writing. So 3-port devices normally. So these are number 1, we are going to say that is a E plane T. Okay, and second is H plane T. Okay, so one by one we are going to see these different types of 3-port junction based passive devices. Okay, so the E plane T or H plane T, they are simple example of 3-port passive microwave junctions. These junctions are simple in the shape of English capital letter capital T. and therefore they are simply being called as a T's. So why they are called as a T? Because their construction shape is going to take the shape of English capital letter capital T. So that's why these three port devices are very commonly known as a T devices, right? Now these T devices are reciprocal circuit, and with wide variety of application they suffer with a limitation of lack of isolation between the output port. Okay, so normally all the three ports are reciprocal of each other. The electrical behavior of this three port junction device can be described by important theory. Okay, the short circuit can also be placed in one of the arm of the out of three junctions, and no power can be transferred to the other two arms. Okay, now here in these particular three port devices, as it consists of a three port structure, it is very important to consider property of electrical symmetry and electrical anti-symmetry. If you recall, during the studying of the properties of a scattering matrix, we defined those properties, electrically symmetrical and electrically anti-symmetrical properties. So during that time, that property we studied with the help of taking example of three different ports. Okay, so wherein two ports are going to be said electrically symmetrical with the third port, okay, if it satisfies certain condition. On the other hand, the given pair of a two ports can be electrically anti-symmetrical with the third port. Okay, so these properties very frequently we are going to make use of. Right, now we will go ahead and we will see the typical construction of H-plane T. Okay, so here first of all we will see what is H-plane T. Okay, so what I will do is I will take the image from the library over here. Okay, so what I will do is I will put the image over here. This is a particular H-plane T, how it look like. Okay, so here you can zoom in, and this is a typical construction of the H-plane T if you observe. Right, so what is a H-plane T? The H-plane T is a three port junction. If you observe in the diagram over here, in the first diagram over here, what it consists of? It consists of three arms. Okay, so out of these three arms, two arms are said to be in linear direction. So here the port number 1, I will change the color. So here the port number 1 and port number 2, they are in front of each other. Okay, and these two ports are said to be present in the front arm or collinear arm, and the other arm is called as a side arm. So the port which is located in the side arm is port number 3. Right, so the two arms we call it as a collinear arms, and the collinear arms are the arms which are located in front of each other. Right, so these are the two collinear arms, and the arm which is located perpendicular to the collinear arm we call it as a side arm, and in the side arm we have a third port over here. Right, now this particular T junction is also known as a shunt arm. Okay, so here this T junction is also known as shunt arm. So here the name to the H-plane T is also a shunt arm, shunt T. It is also known as a term shunt T because a parallel port is connected to the collinear arms of the two ports. Okay, so in figure B, if we see, there is a field configuration of electric field lines which are shown when the signal is getting propagated through this junction based device, how the electric fields are getting oriented. Okay, and diagram C over here, it indicates symbolic representation of the H-plane T, where port 1 and port 2 they are located along the straight line, and normally this we call it as a collinear arm, and the port 3 which is located perpendicular to it, and we call it as a side arm or H-plane arm. Okay, and the equivalent circuit you will find in figure number D over here. So this is the equivalent circuit. So how the equivalent circuit is represented? The equivalent circuit is represented in the form like a shunt stub. Okay, so that's why this 3-port device is also known as a shunt type of T, right? So here I will explain you what are the basic properties of these junctions. Now this particular device is also called as a current junction, or the other name is also known as a shunt junction. Okay, usually the collinear arms are given with the ports port 1 and port 2. So here in figure you observe that port number 1 and port number 2 are connected in front of each other, and port number 3 is connected in perpendicular to these two ports. Okay, so the T junction can be fabricated. How this is constructed then? You can take two different rectangular waveguides, and these two rectangular waveguides you connect perpendicular to each other, and we will get the H-plane T. Okay, so it is constructed by making use of two pieces of a rectangular waveguide. Okay, and then the joining point where the two rectangular waveguides are connected, the aperture is made in the wall. Okay, and the two pieces of the waveguides are then connected. Okay, so the T can also be made using a coaxial line. So instead of waveguide, you can also make use of a coaxial cable over here, right? So what is the important property of this junction? The important property of this particular junction is as follows. Port 3 is perfectly matched. Okay, so port 3 is perfectly matched to the junction, and port 1 and port 2 are electrically symmetrical with respect to port number 3. Okay, so the important property over here, I will type it for the given H-plane. The property is, I will write over here the important property. I will write this property in a bracket so that we can note down property. So the property is port 3, right? Port number 3 is perfectly matched to the junction, right? Port 3 is perfectly matched to the junction, and port 1 and port 2 are said to be electrically symmetrical with port 3. Okay, so if you recall the property of electrical symmetry when we described that during the time of studying the property of scattering matrix, the electrically symmetrical property can be studied using a scattering parameter when we deal with three different ports. Now this is the device which consists of 3 ports, so here we can apply that particular property. And what is the property of H-plane T? The property of the H-plane T is, if the port number 3 is perfectly matched to the junction, then port number 1 and port number 2, these both ports are electrically symmetrical with port number 3. Okay, and what is the property then? Now the property is when the power is incident at port number 3. Okay, let us say over here I will denote. Now if the power at port number 3 is given, let us say the magnitude of power is capital P, then as the two remaining ports, that is port number 1 and port number 2, are electrically symmetrical, then what will happen? This power which we fed at the input of port number 3, it will come out of port number 1 and port number 2 exactly divided by 2. So what we will get at the output of port number 1? So here at the output of port number 1, exactly we will get a power which is divided by 2. So here also at the output of port number 2, we will get a power divided by 2. Okay. So what is happening over here? Whatever power that you fed at the input of port number 3, provided port number 3 is said to be perfectly matched, right, to the junction, then at that time you will get the power at the output of port number 1 and port number 2. Now this power will get equally divided and this power carries the same sign convention, right? So this carries the same sign convention as the port number 1 and port number 2 we said to be electrically symmetrical. Okay, so the important property of H plane T is whenever some input microwave power is fed at the shunt arm or the perpendicular arm, right, at port number 3, this power, whatever power P, that will get equally divided and it will be made available at the output. Okay, similarly the reverse thing is true. So what is the reverse thing? If you apply some power, okay, let us say P1 at port number 1 and P2 at port number 2. So at that time you will get output power at port number 3, which is simply the sum of these two powers P1 and P2. Okay, so this is an important property of the H plane T, right? So here I will write the property of H plane T, important working. So how this circuit or how this device works: when port 3 is perfectly matched to the junction, this condition provided, port 1 and port 2 are symmetrical electrically with respect to port 3, right? So if we feed power if we feed power at port 3, okay, it will get divided equally and made available at the port 1 and port 2. So this is a simple working of H plane T. So how the H plane T works? H plane T works as a microwave power divider, or you can say the H plane T works as equal power splitter with the same sign convention. Okay, so whatever power that you are going to feed at the port number 3, the power will get divided, okay, and it will be made available at the remaining two ports, that is at port number 1 and port number 2. Okay, so these two powers are equal in magnitude and also they do carry the same sign, please remember. So that's why they are known as electrically symmetrical. So the meaning of electrical symmetrical is whatever power output we are going to get at port number 1 and at port number 2, these two power outputs are with the same magnitude as well as with the same sign. That means both are positive. Okay, so this is an important property of the H plane T. Okay, so here what we do is we will now derive the scattering parameter matrix for the H plane T. Okay, so here, as you already know, that this H plane T consists of three different ports. When we analyze this particular device, we need to represent it in terms of scattering matrix. So as it has total three different ports, the scattering matrix is given by a 3 by 3 order, right? So the scattering matrix will consist of total 9 elements and it is a 3 by 3 matrix, right? So 3 rows are there and 3 columns are there, each corresponds to one particular port. So here let us derive the scattering matrix parameter for the H plane T. So next is we will derive scattering parameter matrix for the H plane T. Okay, so we will see the procedure now, how to derive the matrix for the scattering matrix for the given H plane T. Okay, so for that now I will take the handwriting mode, right, and then I will start typing. Okay, so here I will remove this line. Okay, and now I will select my pen and let us start deriving the scattering matrix for the H plane T. Okay, so here for a 3-port device, a scattering matrix, how it is given? So I will write over here, the scattering matrix is given by, see, scattering matrix S is equal to, in terms of 3 by 3 order, it is S11 as it consists of 3 ports, S12, S13, right? Similarly, S21, S22 and S23, and finally S31, S32, S33. Okay, so a scattering matrix for the H plane T is given by a scattering matrix of 3 by 3 order as it consists of 3 different types of ports. Okay, so the first we are going to find what are these S parameters for the H plane T, and that is why we are going to design the scattering parameter matrix for the H plane T. Okay, so at the junction we assume that, so here I will write, we assume that junction is ideal. See, what do we mean by junction? Junction means a space where all these 3 ports are going to combine with each other. Okay, so this particular space, the junction is this particular region over here. Okay, so normally this is called as a junction. Okay, so junction is a space where all the 3 ports are going to meet with each other. Okay, so we assume that the junction is ideal. Junction is ideal. Okay, and all ports are reciprocal. We already know what do we mean by property of reciprocity. Okay, we assume that ports are reciprocal, and we already know that the H plane T is going to follow the property of electrical symmetry. Therefore, what we can write as ports are symmetrical, right? As ports are symmetrical, what we can write? Recall from the property, if the 2 ports are symmetrical. Okay, so what we can write? Sij is equal to Sji, right? For the 2 ports I and J which are not same. Okay, so there are 2 ports, port I and port J, and these 2 ports are said to be reciprocal. Then they should satisfy this particular scattering matrix condition. Okay, and in addition, the port number 3 is also perfectly matched. Okay, so as port number 3 is perfectly matched, so here I will start writing as port 3 is perfectly matched, the reflection coefficient will be 0. Okay, so how the reflection coefficient for the port number 3 is represented in terms of scattering parameter? So the scattering parameter representing reflection coefficient at port number 3 is denoted by S33. So S33 is going to be 0 as port number 3 is said to be perfectly matched. So how we can write this scattering matrix? Let us say this is an equation number 1. So with this modification, with this assumption, how we can write the equation number 1? So this can be written as the scattering matrix S is equal to, right? So S11 as it is, S12 I will write as it is, S13 I will write as it is. Okay, now here what I will follow the property. Okay, so Sij is equal to Sji. Now here I can write S21, so this particular parameter I can reverse the order by using this particular property. Okay, which is followed with 2 different ports. Okay, so here instead of S21, what I will do is I will write S12, right? So similarly S22 as it is I will write, no change. S23 also I will write as it is, no change. Okay, now next is S31 over here. Now this S31 I can write as S13 by again following the same property, S13, right? S32 I will write it as a S23. Okay, and already we know that S33 is 0, so I will put S33 is equal to 0. So you observe equation number 1 and equation number 2. So what we have made the change in equation number 1, we followed these properties and we made S33 is equal to 0, and the scattering matrix is modified from equation number 1 to equation number 2, right? So we will go ahead now in the H plane T. Okay, so here I will write in H plane T. So what we know about the H plane T? Port number 3 is perfectly matched, we already know. Again we need to write it is perfectly matched, right? And it is electrically symmetrical, right? See, if you recall this particular property over here, what we wrote. So port 1 and port 2 are said to be electrically symmetrical with port number 3. So the same property I will write here. It is electrically symmetrical with port number 1 and port number 2, right? So we are going to make use of this particular property now. So port number 3 is electrically symmetrical with respect to port number 1 and port number 2. Thus, how we can write then? We can write, because of this, S11 is equal to S22. Okay, and similarly what we can write, and S13 we can write it as a S23. Okay, so make use of this property in equation number 2 and modify it. So how we can give the scattering matrix then? The scattering matrix S is given by, right? So S11 as it is, S12 as it is, S13 as it is, right? And then S12 second row first element, S12 as it is, S22. Now instead of S22, what I will replace S22 with S11. So I will write S11, right? And S23, now here we can write S23 is equal to S13. So I will write S13. Okay, and similarly here I got S13, right? Here I got S23. Now S23 can be replaced as a S13, and this term, last term, is already 0. Now see how we modified the scattering matrix from equation number 2 to equation number 3, right? So we are going to solve this scattering matrix, and we are going to find values of all these remaining scattering parameters. Okay, so the junction next is, junction is assumed to be lossless. Junction is, I will write, assumed to be lossless, right? It is a lossless junction. Okay, and scattering matrix, whatever we are developing, will obey property of unit and zero property. Okay, so the scattering matrix will obey unitary property. Okay, so you recall from the properties of scattering matrix, what is a unitary property? The unitary property of a scattering matrix are given with two different types. One is a unit property itself, and second property is a zero property. So you recall unitary property of the scattering matrix. Okay, so we apply the unit property to the third column. Okay, so where is the third column? In equation number 3. So first of all I will write applying Okay, so applying unit property, to third column, to column number 3 of equation 3. So here column number 3 over here. So this is the column number 3, right? So apply unit property to column number 3. So you recall what is the unit property when we apply to a particular column? Okay, it is the sum of product of one particular term of a given column with another column with the same column same is going to be equal to 1. Okay, so here what is the first element of column number 3? S13, right? Make square of it. Okay, add with the second element of the third row. The second element of the third row is S13 itself. The sum of square of each term of a given column. Okay, so it is equated to 1. So if we apply this particular unit property to column number 3 of equation 3, we will get mod of S13 square plus mod of S13 square is equal to 1. So if you solve this particular equation, what value we will get? S13 is equal to 1 by root 2. So if you simplify, we will get this value. S13 will get it equal to 1 by root 2. Okay, so what we do is now we will place this value of S13 in equation number 3. Okay, now I will change the color now. So placing values in equation 3 of scattering matrix. Okay, so put this value of S13 in equation number 3. So how the equation number 3 will get modified? S is equal to scattering matrix S11 as it is, S12, and now here S13 I will replace. Already we have got what is S13, it is 1 by root 2, right? S12 as it is. Next term is S11, I will write it as it is. The third term is S13, now I will replace that with 1 by root 2, right? And here in the third row both are S13, so I will replace it with 1 by root 2 and 1 by root 2, and the last term is already 0. Okay, so call this matrix as equation number 4, right? So here we have successfully converted S13 is equal to 1 by root 2. Okay, so what you do is we apply 0 property to row 1 and row 3. So here I will write, now we apply 0 property. Please remember, 0 property and unit property are applicable to the unitary matrix. Okay, so if any particular matrix is said to be unitary, it has to follow two properties, 0 property and unit property. So we already applied the unit property to the column. Now let us apply 0 property. I will write here. Let us apply the 0 property to row number 1 and row number 3. Row number 1 and row number 3 of equation 4, where the equation 4 is a scattering matrix. Okay, so apply the 0 property to row number 1. So first of all, you should know where is your row number 1. So here I will choose this color. So row number 1 is over here, right? And row number 3 is over here. Now we will be applying 0 property to these two rows. Okay, so what the 0 property says, okay, so the sum of product of each term of a particular row with the corresponding term of the other row is equated to 0. Okay, so the sum of product of, so first of all you need to take this particular term S11, the same term of the third row, that is 1 by root 2, take their product. So when I take the product, S11 of the first row multiplied by corresponding term of the third row, that is 1 by root 2. This is the product. So similarly, you go on taking the products of the remaining terms. So plus the second term product, second term of the first row is S12. Take the product with the second element of the third row, that is 1 by root 2 again, plus third element of the first row, that is 1 by root 2, multiplied by third element of the third row, that is 0. Okay, and all this we need to equate to a 0. So what this gives then? S11 upon root 2 if you simplify, plus S12 upon root 2 is equal to 0. Right? So if you simplify this particular equation, okay, so after simplification what we will get is equal to S11 is equal to minus S12, or you can also write S12 is equal to minus S11. So this important feature we will get if we apply the 0 property to row number 1 and row number 3 of the scattering matrix defined with equation number 4. Okay, so here we have got this particular value. Okay, so next what we do is we will apply one more property. Okay, now this time we will apply unit property to row 1. Okay, so here I will write, now we apply unit property to row 1. So we will apply unit property only to row 1. Okay, so row 1 we already know it consists of S11, S12 and 1 by root 2 as a 3 elements. So square of, so multiply the term with itself. Okay, so I will get S11 multiplied by S11, right, plus S12 multiplied by itself S12, plus third term 1 by root 2 multiplied by 1 by root 2 is equal to 1, because it is a unit property. So this particular equation will give me mod S11 square plus mod S12 square. Okay, and here I will get 1 upon 2 is equal to 1. So if you simplify this particular equation, what we will get? S11 square plus S12 square is equal to 1 by 2. Right? So here S11 plus S12 square is equal to 1 by 2. Now recall that we know that S11 is equal to minus S12. So here S12 we can replace. Okay, so S12 we can replace with S11. So here I will get S11 square. Now here instead of S12 I will replace with S11, and anyway making it square it doesn't make any difference. So S11 square is equal to 1 by 2. Okay, so from this what we get is we get the value of S11 and we will get it equal to 1 by 2. Okay, and similarly as S11 is equal to 1 by 2, from this particular relation what we can write as S12 is equal to minus S11 is equal to 1 upon 2 minus. Okay, so here we have got all those values. Now what we do is we will replace all these values in the scattering matrix given by equation number 4. So in equation number 4 we will rewrite these values. So scattering matrix S is equal to, the first element is a S11. So S11 is 1 by 2. Second element is S12, and S12 we have got equal to minus 1 by 2. Third element is 1 by root 2. Already we have received the value. Second row S12 is minus 1 by 2, right? Second element S11, that is 1 by 2. Third element is 1 by root 2. So we are replacing all these values in equation 4, and finally 1 by root 2, 1 by root 2, okay, and 0. So we will observe this particular scattering matrix, and this is scattering matrix for H plane T. This is a scattering matrix for H plane T. So we can make certain observation from this scattering matrix. Okay, so here S33 element is 0. Okay, so what this indicate? As S33 is 0, port 3 is perfectly matched, so that the reflection is 0 and the reflection is represented by S33. Okay, now here S13, right, here this particular term S11, S12, S13, S21, S22, S23, right, S23, then S31 and S32 all are 1 by root 2. Okay, so that means S13 is equal to S23. So what is this particular property? This particular property tells us electrically symmetrical property, right? Electrical symmetry. This electrical symmetry between port 1 and port 2 with respect to port 3, right? So this is an important observation, right? And similarly over here, what we can write, S31 is equal to S32, or you can also write this as S13 is equal to S23, and which again indicates the electrically symmetrical property. And what is the significance of 1 by root 2? Now here these scattering parameters S13 is equal to 1 by root 2. Similarly S23 is equal to 1 by root 2, and so on. So what this indicate? S13 indicate that from 3 to 1. Okay, so while going from 3 to 1, okay, so the signal passing from port number 3 to port number 1, the coefficient is 1 by root 2. Okay, so actually it is the power quantity, and 1 by root 2, that is a 3 dB power quantity. Okay, so it indicates that whenever you feed certain power at port number 3 over here, this power will be made available at port number 1 and port number 2 equally with the same sign. Okay, and thus whatever power, microwave signal power, that you are going to feed at port number 3, it will get splitted equally with the same polarity, and that is the property of H plane T, right? So if we observe these equations carefully and their values, and if we interpret these values, it indicates that the power that we are going to feed at port number 3, it will get equally splitted at the remaining two ports, that is port number 1 and port number 2, and again with the same polarity, and it follows the property of electrical symmetry. Okay, and here we have the terms S11, okay, and in the second row S22, okay, they are equal to 1 by 2, and similarly S12 is equal to S21 is equal to minus 1 by 2. Okay, so all these operations are indicative of the property, and in equation number, let us say this is a 5, in equation number 5 we have successfully derived the scattering matrix for the H plane T. Remember that the H plane T is having the property of electrical symmetry, and as it consists of 3 ports, the given port, the port number 3, is said to be electrically symmetrical with respect to the remaining 2 ports. Okay, and this is the complete derivation of the scattering matrix for the H plane T. Now on the similar basis, let us see how the electric plane T is going to work. Okay, so as you have gone through the theory of H plane T, on the similar basis, the E plane T is also known as a series T, okay, which will oppositely follow the property. Okay, so let us study now the H plane T. Okay, so for H plane T, I will here give the heading as E plane T. H plane T we already saw. Now let us see what is E plane T. Okay, so let us draw the diagram of E plane T. E plane T is already available. I will go to the photo library. I will insert. So this is the diagram of E plane T. What you observe in the E plane T? E plane T, just it is the reverse of the H plane T. Now here we have 2 collinear arms over here, in which port number 1 and port number 2 are located, and we have a third port which is arranged vertically to these 2 ports, port number 1 and port number 2. The vertically arranged port we call it as a port number 3, and figure B shows the electric field distribution in the E plane T, and figure number C will typically show the symbol of electric plane T, and figure number D, it shows the equivalent circuit of E plane T. So if you compare property of E plane T with that of the earlier studied H plane T, we notice that this particular 3-port junction based device is going to behave exactly opposite to that of the H plane T. Okay, so here again we will assume the condition port 3 is perfectly matched. I will write this condition. Okay, port 1 and port 2 are said to be electrically anti-symmetric. With port 3. As in the case of H plane T, we studied that port number 3 is electrically symmetrical with respect to port number 1 and 2. So in this particular case, in the case of E plane T, it is exactly reverse. So if we assume that the port number 3 is perfectly matched, then port number 1 and port number 2 are said to be electrically anti-symmetric with respect to port number 3. Okay, so how it works then? So what is the working of this particular junction based device? The working is similar to H plane T, only the thing is working power is fed at port 3. Let us say this power is denoted by P. Okay, so this power I will write here. This power will be equally distributed, right? It will be equally distributed, or it will be splitted equally and it will be output at port 1 and at port 2 with opposite sign. So this is a very important, with opposite sign. So in the case of H plane T, we saw that whatever power that we are going to feed at port number 3, it will get splitted equally and with the same sign at the remaining ports, port number 1 and port number 2. Here the same thing will take place, but the only change is that in electric plane T, whatever power that we fed at port number 3, this power will get splitted equally at port number 1 and port number 2, but the sign or the polarity of these two signals are going to be opposite. So if you observe figure number B over here carefully, at port number 1 and at port number 2, see how the electric fields are oriented. The orientation of electric field at port number 1 and port number 2, they are not same, but they are exactly opposite, and that's why the output that we are going to get at port number 1 and port number 2 are exactly same, but they are opposite in polarity. Okay, and that's why this particular circuit or junction based device is supposed to be following the property of electrically antisymmetric. Okay, so similarly what we do now is we will derive the scattering matrix for the E plane T. We will use the same concept which we utilized over here in order to derive the scattering matrix for the H plane T. So we will use the same steps over here, and let us see what scattering parameter matrix we will get for the E plane T. Okay, so first of all we will write a 3 by 3 scattering matrix. So for a 3-port device, the scattering matrix, I will change the color. The scattering matrix for a 3-port is given by S is equal to, again same, S11, S12, S13, S21, S22 and S23, and similarly the third row S31, S32 and S33. This is a generalized 3 by 3 scattering matrix representing any 3-port network, and here the example of 3-port network is our E plane T, right? So let us start with this particular matrix. Say I will write here the property in E plane T. In E plane T, what we know that port number 3 is anti-symmetrical with respect to port number 1 and port number 2. So this is an important property in E plane T that we know. So with this property, what we can establish a relationship between the scattering parameters. If this is a property, then S11 is equal to S22, okay, and we can write that S23 is equal to minus S13. Okay, so with this modification we will modify the scattering matrix which is given in equation number 1. Now why this S11 is equal to S22? Because it is perfectly matched. The port number 3 is perfectly matched, so the remaining ports are also perfectly matched, right? And S23 is equal to S13 because this is a particular indicating property of antisymmetry, right? If you recall from the theory of scattering matrix, I will write here. So you make change in equation number 1 the scattering matrix. So how the scattering matrix will become then? S is equal to, how we can write then? We can write S11 as it is, S12 as it is, S13 as it is. In the second row, S21 I can write as a S12, right? Now S22 I will replace with S11, right? And S23 I will replace with minus of S13 because of electrical antisymmetrical property. And similarly in the third row, S31 I will write as a S13, S32 I can write as minus S13, right? And S33, as the third port is perfectly matched, I will write it as a 0. Okay, this is equation number 2. Okay, the junction is ideal and it should be a lossless. So here I will write as junction is assumed to be ideal and lossless. The scattering matrix or S matrix I will write. The scattering matrix will follow unitary property. Again, we assume that this particular matrix is ideal and lossless, and that's why it is going to follow the property of unitary conditions. We already know how the unitary property of the scattering matrix is denoted. The unitary property of the scattering matrix is bifurcated into two types. One is a zero property and another is a unit property itself. Okay, so it will obey unitary conditions. As we assume this particular scattering matrix will follow the unitary condition. Okay, so what we do is we apply unit property to column 3. Apply unit property to column 3. Of this particular matrix. So I will change the color. So where is the column 3? At the column 3 you apply the unit property of unitary matrix. Okay, so what the unit property says, multiplication of the term of any particular column, so that is S13 with itself, S13 into S13, plus multiplication of the term, second term with itself, S13, it is a minus, multiplied by itself, S13 minus, okay, plus 0 is equal to 1. So how you can write this equation then? You can write this equation S13 mod square plus S13 mod square is equal to 1. So if you simplify this particular equation, what value we will get? S13 we will get is equal to 1 by root 2. Right? So what we do is we replace this value of S13 in equation number 2 and we will rewrite the matrix, and the matrix will become S is equal to S11 as it is, S12 as it is. Now S13 I will replace with 1 by root 2. Now S12 I will write as it is, S11 I will write as it is, S13 I will replace with minus 1 by root 2. Now S13 1 by root 2, again minus of 1 by root 2, and it is 0. And now here we are only left to find two terms, that is S11 and S12. Okay. Now what we do is, next we apply, now here I will write 0 property, we apply 0 property to row 1 and row 3, to row 1 and row 3. So first of all you highlight where is your row 1. So your row 1 of matrix is this one and row 3 is this one. So what you do is you apply the 0 property to row 1 and row 3. Okay. So what is the 0 property? I will write here the first term of first row multiplied by first term of the third row. Take the summation of all such terms of row 1 with row number 3 plus S12 multiplied by minus of 1 by root 2, right, plus 1 by root 2 third term of first row multiplied by third term of third row is equal to 0. So what this equation gives then? This equation gives S11 by root 2 minus S12 by root 2 is equal to 0. So what this gives then? This gives us S11 is equal to S12. So this important thing that we are going to get from this particular step. Okay. So next what we do is we will apply one more and last property. We apply unit property now. we apply unit property to row 1. Only we will apply the unit property to row 1. Okay, so what is the unit property to the row 1? It is sum of product of each term with itself is equated to 1. So row 1, the first element is S11, take the multiplication with itself and take such a summation of all the terms in row number 1 into S12, right, plus the third term 1 by root 2 multiplied by 1 by root 2 is equal to 1. Okay, so here what we will get, S12 square, sorry, S11 square, right? So this gives mod S11 square. The second term I will get mod S12 square. The third term that I will get 1 by 2 is equal to 1. Now from here we know that S12 is nothing but S11. So here I will replace S11 square. Now S12 I will replace with S11 from this relation, plus 1 by 2 is equal to 1. So what this particular equation gives, then if you simplify, what this will give? This will give S11 is equal to 1 by 2, and that is same is equal to S12. Okay, so we know what is the value of S11, we know what is the value of S12. Okay, so you replace these values of S11 and S12 in equation number 3, and hence equation number 3, if we substitute the values, what we will get? It is S11 is 1 by 2. Okay, and similarly S12 is also 1 by 2. S13 is already 1 by root 2. Second row, S12 is 1 by 2. S11 is again 1 by 2. Right? Third term is minus 1 by root 2. And in third, 1 by 2, 1 by root 2, 1 by root 2, it is minus 1 by root 2, and last term is 0. Okay, so let us call this as an equation number 4. Okay, let us call this an equation number 4. So equation number 4 completes the scattering matrix for the electric plane T. Now the observations are again similar to that of the H plane T. Now here we observe that S33 is equal to 0, this particular value. Okay, it is 0 because we assume that port 3 is perfectly matched. Okay, and the remaining term will be either 1 by root 2 or it will be 1 by 2. Only the change in E plane T with respect to H plane T is it is going to behave oppositely. Okay, so whatever power that you are going to feed at port number 3, this power will get equally splitted and it will be outputted at port number 1 and port number 2. But the only thing in the case of E plane T is that this power will come with opposite polarity with respect to each other. While in the case of H plane T, the power that you are going to get at the remaining two ports are equal, and it is also equal in terms of polarity or sign convention. So these are the two different types of T's which are very commonly used in microwave circuit, especially for splitting of the microwave signal. Okay, now you may ask me what is the application, typical application of these 3-port junction devices for which we just right now developed the scattering matrix equation. See, the rectangular waveguide T's are used as a tuner circuit by placing the short circuit in the symmetrical arm. So these devices can be used as a power dividers, and these can also be used as a adders in the duplexer circuits. Okay, so as an application of these circuit as a tuner, a movable short can be placed in the side arm. The input connected to one of the collinear arm port and the output is extracted from the other collinear port. Okay, the susceptance offered by these junctions is going to depend on the depth of the insertion of the side arm. So if we change the susceptance, this change in the susceptance can be utilized for impedance matching operations, right? Now these devices are extensively used in the applications like power divider. Okay, in the power divider you can combine and you can divide and you can split the power also. Another important application of using these 3-port T's are in the duplexer circuit. So what is a duplexer circuit? Duplexer is a device which allows a single antenna to be used for both purposes. The single antenna, it will get facilitated as a transmitter as well as it is a receiver. So that can be done with the help of using these 3-port junction devices. Okay, during the transmission process the antenna will get protected, okay, the receiver, and the receiver will be avoided to burn out or damage. Okay, and during the reception the channel will echo the signal correctly into the receiver instead of a transmitter. Okay, so these 3-port microwave passive junction based devices, they find their extreme usefulness in circuits or systems like power divider, combiners, okay, splitters, and even in duplexer circuit. Okay, so what we do is next we will go ahead and we will add one more port into the existing structure, and that structure will now give us a 4-port device. Okay, so a 4-port device can be constructed by combining two 3-port devices, and this 4-port device we normally used to call it as a magic T, or it is a combination T. When we combine this E plane T with H plane T, we will get a 4-port device, and this 4-port device we normally call it as a magic T or a hybrid T. Okay, so let us see how this 4-port device is constructed by using the combination of two 3-port devices. So here we'll go ahead and let us start studying the 4-port device. So I will write over here 4-port device. So 4-port device can be constructed by H plane T, adding this with E plane T. Okay, so when you add H plane T with E plane T, we will get a hybrid T. So the 4-port device normally called it as a hybrid junction. Okay, hybrid junction, or it is also known with another name as magic T. Okay, so why it is called magic we will see in a time. Okay, so I will take the diagram of how this magic T look like, which normally consists of a 4-port device. Okay, so here this is a diagram of a 4-port device. So what we observe over here, distinctly there are 4 ports, port number 1, port number 2, which are located in the collinear arm, and there are 2 additional ports. One port is located vertically. Okay, so this port number 3 is an electric arm port, okay, which is oriented along the E plane, and H plane is oriented along the port number 4. So here along the port number 4 we have the H plane, and along the port number 3, which is oriented vertically, we have the electric plane, and the 2 common ports are located along the same line, and we call them as a collinear ports, and these are indicated as a port 1 and port 2. How it is symbolically represented? It is symbolically represented in which is shown in figure B. Okay, so the electric field lines are shown for the magic T. So this particular 4-port combination is constructed by combining the electric plane T with H plane T, and this hybrid junction, which consists of a 4-port, we normally call it as a magic T junction. Okay, so the magic T is an important 4-port 4-arm junction which is formed by attaching the side arm to the slot cut in the narrow wall and the broad wall of the piece of the waveguide. The arm which is connected to the slot to the broader wall of the waveguide is called as E plane T. So the broader dimension of the rectangular waveguide is this one. So the arm which is connected along the width, we normally call it as the electric plane. Okay, and the arm which is connected along the height, this particular shorter dimension. So here we already know that if this is the rectangular waveguide over here, right? So this is the width, right? And this is a typical height. And we already know what is the relationship. Width is greater than height. Okay, so if you connect a port in this way, if you connect a port along the width, along this one, in this way, right? So this will give the H-plane arm in this way. Okay, and if you connect a port along the height in this way, it will give the H-plane arm. So the E-plane arm is oriented vertically along the broader dimension, and the H-plane arm is oriented along the smaller dimension, that is along the height. The arm which is connected to the other slot in the narrow wall waveguide is known as a H-plane arm. Okay, so the E-plane arm and H-plane arm, how they are connected with the collinear arm is in front of you. The electric field line, the electric field configuration is also shown over here. Okay, so actually this is a simple combination of E-plane T with H-plane T. E-plane T and H-plane T both consist of 3 ports. So if you combine them together, we will get a new device, and this device will then consist of 4 different ports. Okay, out of which 2 ports are located in the collinear arm, and these are port number 1 and port number 2. Okay, so the port which is located vertically to the broader dimension, we call it as the electric arm. Okay, and the port which is located along the shorter dimension of the waveguide, we call it as a H-plane arm. Okay, so these ports are shown in the figure: port 1, port 2, port 3 and port 4. Okay, so what is the application of this particular 4-port device? The typical application of this 4-port device is it is used as a power divider circuit. Okay, so whatever job is being accomplished by using H-plane T and E-plane T, the same job can be accomplished using this combined device. Okay, so you can divide the power equally and also with the same polarity, as well as also with opposite polarity. Okay, so both things you can perform using this magic T power divider circuit. As the source is connected to one of the side arms with a matched termination at the other side arm port, the load impedances are connected to the ports of collinear arms. The magic T exhibits certain properties when the terminations are interchanged between the side arm ports and the collinear port. Okay, so this magic T is basically a hybrid junction. Why it is called as a hybrid? Because it is constructed by combination of E-plane T and H-plane T. Okay, so this hybrid, the power will get divided equally between the output ports. Okay, so the power that will get divided equally at the output port, they can exhibit a phase shift of 0 degree or 180 degree. The main advantage of this particular circuit is the fact that the power delivered to one of the output port is independent of the termination at the other output port, provided the remaining ports are considered to be terminated in a matched configuration. Okay, so normally what we expect is the input power is moving entirely from one collinear port to another collinear port, and from one side arm port to the other side arm port. But normally in the magic T, what happens? See here how I describe. See, normally what happens during the operation is we expect that when we feed the power at arm number 1 at port number 1, we assume that this power will flow from one collinear port to other collinear port, and this power will come out of port number 2. Okay, so normally this is our assumption, and it will come from one side arm port to another side arm port also. So this power whatever we are feeding at port number 1 will come at port number 2, and similarly we normally assume that it will also come at output port number 3 as well as output port number 4. This is a normal assumption. So whenever we fed the power input at port number 1, we normally assume that this delivered to port number 2, port number 3 and port number 4. This is a normal assumption. Okay, but actually the thing is different over here in this magic T. So that's why this particular operation we call it as a magic T. So for this particular device, this type of power delivery will not take place. Okay, so what happens then? Now in this particular circuit, in reality, no power flows from the collinear port to other collinear port. So that means, suppose this is your port 1 and this is your port 2. Port 1 and port 2 are located in the collinear arm. Port 3 is located and we call it as the electric arm, and port 4, which is located, we call it as a H arm, okay, or H plenty. So whenever we feed certain power at the input of port number 1, the power will not made available at port number 2. Okay, so normally this will happen in the magic T or the hybrid junction. Okay, the power will get delivered at port number 3 and port number 4 only. Okay, so let us see how this is. Normally, in reality, the power flows from one collinear port and it will not reach to the second collinear port, and it also from one side arm port to the another side arm port. Okay, so in reality, none of the power flows from one collinear port to another collinear port. That means when you feed the power at port number 1, this power is available at port number 2, that is in a collinear port, and also from one of the side arm port to other side arm port. Okay, so none of the power will come from collinear port to any other port. Okay, so this is actually what is that we are not expecting. Okay, so that's why this particular operation of the junction, 4-port junction, is called as a magic or trick. Okay, so that's why it is called as a magic T. So normally when we feed a power at port number 1, we assume that it should come at port number 2, 3 and 4, but it will not happen. It will come at the output of port number 3 and port number 4, and it will avoid the output signal at port number 2. Okay, and this is what we call it as a different operation, and that's why this particular circuit is called as a magic circuit. Okay, now how this particular circuit operates. Okay, so we say that a match source is connected to the H arm and the electric arm is matched terminated, and the remaining collinear ports are connected to the mismatched load. Okay, if all the ports are perfectly matched to the junction for the signal in the collinear port, okay, it will get splitted equally between electric arm and magnetic arm. Okay, so if we assume that all the four ports are matched to the junction, and whenever we feed certain power at the input of port 1, this power will get splitted across electric arm and magnetic arm. Okay, but it will not come at the output of port number 2. Okay, so the power at electric arm and the power at magnetic arm are exactly P by 2, that is they are exactly halved, they are divided exactly by 2. Okay, so the signal which comes from the electric arm has negative polarity or opposite polarity with respect to that the signal which we are getting from the H arm. Okay, so the signal into the arm will get split equally between the collinear ports, and the output through them will be in phase when the collinear port arms are going to be same. Okay, so here the purpose of using this particular device is, as we saw in the case of E plane T and H plane T. Okay, so if you want to combine the power or divide the power, and also if you want to do this particular job such that the splitted power with equal polarity or the splitted power with opposite polarity, if you want to implement this particular functionality in altogether one particular device, then we are going to make use of this 4-port device. We call it as a hybrid T or magic T. Okay, so the next important part is to develop a scattering matrix solution in order to describe the behavior of this 4-port magic T. Okay, so in the next process what we will do is we will start deriving the scattering parameter for this 4-port device. Now as we already know, this is a 4-port device. As 4-port device is characterized by a scattering matrix given with 4 columns and 4 rows. So the scattering matrix for the magic T is of order 4 by 4. Okay, so I will write the scattering matrix now. Let us say S is the scattering matrix for this 4-port device, and it is denoted by 4 rows and 4 columns: S11, S12, S13, S14. Similarly, S21, S22, S23 and S24. Third row, S31, S32, S33 and S34. And finally the fourth row, S41, because it has a 4 ports, S42, S43 and S44. Okay, so we need to find all these scattering parameters. That is our job, or that is our aim. Okay, so first of all, how we start? We start that I will write here port number 1, 2, 3, 4, all ports. I will write here all ports are assumed to be perfectly matched to the junction. To be perfectly matched to the junction. If we assume this particular condition, then what we can write? If all the 4 ports are perfectly matched to the junction, then we can write S11 is equal to S22 is equal to S33. Reflections are 0, right? S44 is equal to 0, right? So with this, all reflection coefficient at all the 4 ports from port number 1 to port number 4 are perfectly matched. So that's why they don't exhibit any reflection. So that's why these S parameters are 0. So then how the scattering parameter will become? So this matrix will become S11 is 0, right? S12 as it is, S13 I will rewrite it, and S21, S22 is 0. All the diagonal elements will become 0, right? S32, and this diagonal element will become 0, S34, and S41, S42, S43, and this diagonal element now will become 0. Okay, this has been reduced to this particular matrix. Next, what we study here, that port 1 and port 2, I will write here port 1 and port 2, and port 3, 4 are assumed to be perfectly isolated. They are assumed to be, all are assumed to be perfectly isolated from each other. So that means port 1 with 2, okay, and port 3 with port 4. So these ports are said to be isolated from each other. So if this is the condition, then what we can write? Property of isolation S12 is equal to S21, right, is equal to 0, because they are isolated from each other. And similarly S34 is equal to S43 is equal to 0. Now put these values of scattering parameter in the above equation 2, and what we get? The equation for scattering matrix, S is equal to 0, S12 is 0. What is S13? As it is, S14 as it is, right? S21, now it is 0. S22 is already 0. S2 as it is. S24 as it is. S31 as it is. S32 as it is. S33 is 0 and S34 is now 0. S41 as it is. S42 as it is. Okay, S43 is now 0 and S44 is already 0. Okay, now we have reduced the scattering matrix still further. Okay, so we will get this particular scattering matrix. Now what we do, the next step is, as the junction is ideal, as the junction is ideal and it is reciprocal, right? And it is reciprocal, therefore matrix is symmetrical. Matrix is symmetrical. So for the symmetry property, what we can write? Sij is equal to Sji for I which is different from j. So this you should know. Therefore what we can write? S13, we can write it as a S31, right? And similarly S14, we can write it as a S41. And what we can write similarly? S23 can be written as S32 and S24 can be written as S42. Okay, so we replace these terms in equation number 3 with the scattering parameters. So it will be given as a scattering parameter S is equal to first term 0, second term 0, S13. S13 we will write as it is, right? S14 we will write as it is. These two terms are 0. Now S23 we will write as it is. S24 also we will write as it is. Now S31. Now the S31 will replace with S13. So I will write here S13. S32 I will replace with S23. So I will write S23 over here. These two terms are 0. S41, okay, I will replace with S14. S42 I will replace with S24 and these two terms are already 0. Okay, let us call this as a modified equation number 4. Okay, so now we will apply individually the electric arm condition and magnetic arm condition separately. Okay, so first of all, in the magic T or in hybrid T, what we know? In the hybrid T, we know that electric arm is located, yes, here in the diagram if you see where the electric arm is located along port number 3. Electric arm is located at port 3. Okay, and it is anti-symmetric, right? Being it is a electric port, it is anti-symmetric. It is anti-symmetric with respect to port number 1 and port number 2. Okay, so here port number 2, I should write it as a port number 2. We know that here in the diagram the electric arm is located along the port number 3, so that's why it will be electrically anti-symmetric. It will follow that property and it will be anti-symmetric with respect to collinear arms. That means anti-symmetric with respect to port number 1 and port number 2. So what we can write this particular property as? Then we can write that S23 equal to minus of S13 because it is electrically anti-symmetric. or we can write S13 is equal to minus S23, because port 3 is electrically antisymmetric with respect to port number 1 and port number 2. Okay, so we will include this change in the above equation number 4, and we will rewrite the scattering matrix as the first two terms are 0. S13 we will write as it is, S14 we will write as it is. These two terms of the second row are 0. Now S23 over here, this S23 we will replace with minus of S13, right? And S24 we will write as it is. Okay, now here S13 as it is. Now S23 over here, this we can replace with minus of S13. So these two terms are again 0. Okay, and finally S14 I will write as it is, and S24 also I will write as it is, and these two terms are 0. So what I did in this particular step? In this particular step, I applied the property of anti-symmetry for the port number 3, which is said to be anti-symmetric with respect to port number 1 and port number 2. Okay, now next property we will apply for the H-plane T. So here again we will write in hybrid T, the H arm is located at port number 4. Okay, so if you recall this particular diagram of magic T, now here along the port number 4 H arm is located. So it will follow the property of symmetry then. So it will follow the property of symmetry. So port number 4 is electrically symmetrical with respect to port number 1 and port number 2, as these two ports are collinear. Okay, so port number 4 is electrically symmetrical with respect to port number 1 and port number 2. Therefore, we can write S14 is equal to S24. Now put this value in the above equation of 5. So the scattering matrix will reduce to 0, 0. Okay, now it is S13. Okay, now here S14 as it is, 0, 0 again, minus S13 as it is. Now instead of S24 over here, we can replace that with S14. Then here again S13 as it is, minus S13 as it is. These two terms are 0. Now S14 first element as it is. Now S24 over here, I will replace with S14 because of symmetry property of the H arm in port number 4, and these two terms are again 0. Okay, and then our matrix has been reduced to this particular form. Okay, now next what we are going to do is we are going to assume that the junction is ideal and lossless, and we say that the scattering matrix for this H-plane hybrid T is going to follow the unitary properties. So the next what we are going to do is we are going to apply the unitary properties. Okay, so here I will write as junction is said to be lossless, the S matrix follow unitary conditions. It will follow the unitary condition. Okay, so what are unitary condition? There are two conditions. First condition is 0 property, and second property is itself a unit property. Okay, so what we do is now we apply, I will write here, apply unit property to column number 3 of above matrix in equation 6 Okay, so what we do is we will apply the unit property to the column number 3 of the matrix which is given by equation number 6. Okay, so what is the unit property? Okay, so the product of the term with itself, and when you go on taking the summation along the same column, it has to be equated to 1. So if we apply the unit property to column number 3, so I will denote where is the column number 3. Column number 3 is over here, right? So apply the unit property to this particular column. So what we can write is S13 multiplied by itself. Okay, go on taking the self product in this particular way. So second term is minus S13 multiplied by itself. Third terms are 0 and fourth term is also 0, and this is equated to 1. So what we get here, S13 mod square. Now here also we will get S13 mod square is equal to 1, and when you simplify it further, I will get S13 is equal to 1 by root 2. Okay, S13 is equal to 1 by root 2. So what we do is we will replace this value of S13 in equation number 6, and we will rewrite the matrix. So this matrix then becomes S is equal to first value is 0, second value is 0, third value is S13, it is 1 by root 2, S14 as it is, 0, 0. Now minus S13 means minus 1 by root 2, spacing the value S14 as it is. Now here S13 is 1 by root 2, minus S13 is minus 1 by root 2, right? And these values are again 0, 0. Now S14 is as it is, S14 as it is, and here 0, 0. Now the only unknown in this particular matrix is S14, and that can be found by using the another property of unitary condition. So here the only unknown left is S14, sorry. Okay, so how to find that? Again, what we do is we apply unit property now. We apply unit property, not zero property. We will apply unit property to column number 4. To column 4 of above equation or above matrix, which is given by equation number 7. Okay, so here I will highlight column number 4. This is a column number 4. Now what we do is you apply unit property to column number 4. Again the same, S14 multiplied by itself, go on taking the summation of all the terms in that particular column. In this way, it is a 0 already, and it is also 0, and it is equated to 1. So this will give me S14 square plus again S14 mod square is equal to 1. And when I simplify this, I will get S14 is equal to again 1 by root 2. Okay, so I will replace this value of S14 in the original matrix, and the final matrix is going to be 0, 0, 1 by root 2, and S14 is also 1 by root 2. Again it is a 0, 0, minus 1 by root 2, 1 by root 2. 1 by root 2, and second is minus 1 by root 2, and these two terms are 0, and here 1 by root 2 and 1 by root 2, and these two terms are 0. So what we observe from this equation, this is the final equation number 8, and equation number 8, whatever scattering matrix we have developed, this is the scattering matrix for the hybrid junction. Okay, so if we observe this scattering matrix carefully, it shows us that it has simply combined the result of E plane T and H plane T together into its combination. Okay, so hybrid T or hybrid junction or magic T, one at the same terms. This particular device is a 4-port device, and it is constructed by combining H plane T and E plane T together. And the scattering matrix, when we formulate the scattering matrix for this particular device, it is just the combination of the scattering matrices for H plane T and correspondingly E plane T. Okay, so I hope you understood today the junction based devices. We started with the 3-port junction based devices. We explained you the how the H plane T works, important property, and then we go over E plane T, and we saw that the behavior of the E plane T is exactly opposite of that of the H plane T. And thereafterwards we combine these two T's together in order to give us a new device which consists of 4 ports rather than a 3-port, and that device is a magic T. Okay, so on the similar basis here we can have one more particular device which consists of again 4 ports, which is analogous to the magic T. Okay, so whatever the equations, formulation of scattering matrix we have developed for the magic T, on the similar basis we can formulate the equation of scattering matrix for the another device, and that device which again has a 4-port, and this is analogous to a magic T, we used to call it as a hybrid ring. Okay, and this hybrid ring is sometimes also known as a rat race type of a junction. So the next 4-port device in a simple time or in a brief short time that we are going to see, that is again a 4-port device, and that device we call it as a hybrid ring. Please remember, this hybrid ring is similar or analogous to magic T. So this hybrid ring is also known with some other name known as a rat race junction. Okay, why it is called rat race junction? Because it visually appears as a indicative of a rat race type of cage. So that's why this particular circuit is normally called as a rat race junction, or the other name to this particular device is a hybrid ring also. So let us see what is this rat race junction or the hybrid ring. Again, please remember that this hybrid ring is analogous to magic T only. Okay, so let us insert the image of rat race junction, this one. Okay, so here you can clearly visualize in this particular diagram. Okay, so this rat race junction can be designed in either H plane T or in E plane T. So whenever you design the rat race junction in H plane T, you need to orient it in a horizontal plane. So this is a horizontal plane. Okay, in other words, if you design the rat race junction in a vertical plane, so it will become E plane rat race junction. So similar to H plane T and E plane T, there are again 2 types of rat race junction based on how you are going to orient that rat race junction. If it is oriented horizontally, we call it as a H plane rat race junction, or when it is oriented vertically, we call it as a E plane rat race junction. Okay, so let us briefly see, we are not going to derive the detail, but the deriving the scattering matrix for this particular rat race junction or the hybrid ring is simple and straightforward. Okay, so let us go to the theory. What is this rat race junction? This hybrid ring or rat race junction is a 4-port device. Okay, so we observe over here there are always a 4-port. This is a port 1, port 2, port 3 and port 4. Okay, and similarly over here we have port number 1, port number 2, port number 3 and port number 4. See, in both of these configuration, this is a 4-port device similar to magic T, right? So this 4-port device is fabricated from the sections of a rectangular waveguide. It essentially consists of a waveguide ring having the mean circumference length of 1.5 lambda. Okay, so if you go across all the periphery of this particular circular ring, you will find that 3 lambda by 4. So the total periphery I will write over here. Or if you completely make one trace along the circular dimension of this rat race junction, the total circumference I will write here, it is equal to, say, half of the circumference is indicated over here, it is 3 lambda by 4. Now here the lambda is replaced with a lambda g that indicates the guide wavelength. So 3 lambda g by 4 plus this much is lambda by 4 we'll write lambda g by 4. Again, the spacing between port 3 and port 2 is again lambda g by 4. And such a 3 section we will get lambda g by 4, lambda g by 4 and lambda g by 4. So port 1, port 2 and port 3 and port 4 all are separated from each other by a distance of lambda g by 4. So here it is a 3 lambda g by 4, okay, and 3 lambda g by 4. Again you can write in this way. So total 6 lambda g by 4. So here you can write 3 lambda g by 2 or indirect 1.5 lambda g. So the total circumference of this particular device is always evaluates to a guide wavelength of 1.5. Please remember. So this hybrid ring or rat race junction circuit is capable of sustaining the standing waves, and the waveguide sections or arms are connected in a manner such that proper intervals are set by means of series and parallel junction. This junction can be designed either to have a series or parallel junction. Okay. In the case of a parallel junction, the structural arrangement usually consists of the pieces of rectangular waveguide bent in the H-plane. Okay. So this particular H-plane is also known as a parallel junction. Okay. So the parallel junction rat race is also known as a horizontal plane. Okay. On the other hand, when the sections of the rectangular waveguide are bent in the E plane, okay, then it will call it as a perpendicular junction, which is also known as a vertical plane or E plane, perpendicular junction. So the rat race coupler can be designed either in a horizontal plane or it can be designed in vertical plane also. Okay. Now, what is the typical working of this particular device and why this particular device is used? Please remember, this device is going to give the same functionality as the magic T is going to offer to us. Okay. So how this particular thing works, let us see. If we assume that there are no reflection from the termination from the any of the arms, then any arm is coupled to the other two arms, but it will not couple to the fourth arm. The meaning of this, if port 1 is matched to the junction when port 2 and 4 are match terminated. Okay. So here I will denote like this. Let us say this is the hybrid ring structure, right? And this is port 1, port 2, port 3 and port 4. This is a port 1, port 2. I am just denoting for the simplicity, port 3 and port 4. Okay. So when port 1 is matched to the junction, when this is said to be matched, then the adjacent ports are said to be automatically match terminated. So the adjacent port to port number 1 is port number 2, and the another from this side, the adjacent port to port number 1 is port 4. So port 4 and port 2 are also get automatically matched when port 1 is matched. So what is the meaning? When one port is matched, their adjacent ports from the two sides, they are also assumed to be matched. Okay. So similarly, if you take the example of port 2, what are the adjacent port to port number 2? That is port number 1 and port number 3, right? So this is way, this is considered in a similar way. Okay. So when a signal enters to port number 1, so when a signal enters into port number 1 with a power P, okay, so it will get splitted equally at port number 2 and 4. Okay. So I will redraw it over here again. Let us say this is port, these are the ports. Okay. Port 1 will go clockwise, port 2, port 3 and port 4. Okay. So if the signal, micro signal enters at port number 1, so what are the two adjacent ports to port number 1 from either side? From this side, the adjacent port is port 4, and from this side the adjacent port is port number 2. So this power of the micro signal, when it enters at port number 1, it will get splitted equally at port number 2 and port number 4, right? It will get splitted equally at adjacent port, okay? And there will not be any power flowing at port number 3. Okay, so this is a particular working of this hybrid ring junction. So when the hybrid ring is excited with a certain microwave power at port number 1, this power will get divided equally, splitted equally. So it will become P by 2 and P by 2, and it will be made available at the output of port number 4 and port number 2. And there is no power at port number 3, right? So this applies the same, okay? And here the port number 1 as an input port, and the signal will get equally splitted at port number 2 and 4, okay? And similarly, when the signal enters to port number 2, on the other hand, I will show in a different color. Let us say we'll choose this green color. When the signal enters at port number 2, then it will get divided equally at what ports? Again, what are the adjacent ports to port number 2? Port number 1 and port number 3. And there is no power at port number 4. Okay. So the waves at the port exhibit phase difference of 0 degree or 180 degree respectively. Okay. So if the input signal is applied at port number 1, the output will appear at port number 2 and port number 4. And these output differ by 180 degree. Okay. So this power which we input at port number 1 will get divided equally, and it will be made available at port number 4 and port number 2, such that there is a difference in their polarity, but the magnitude is same. So that means the power will get splitted equally but with opposite phase. Okay. On the other hand, if the input is applied at port number 4 reversely, okay, then the output will appear at port number 1 and port number 3. Okay, and again these two outputs are equal and opposite in the phase. Okay, and the same is true no matter at what port you are going to apply, it is going to skip the front port. And as on when you apply any input power to any particular port, it will get divided equally and it will be made available at the two adjacent port and not at front port. Okay, so this is a typical working of this particular hybrid ring, right? So the wave which is fed to port 1 cannot appear at port number 3, because the difference of the phase shift, see, if you travel along, so this all these ports are separated with a lambda by 4. Okay, so if why you are not going to get any signal at port number 3 is, if you travel along the p direction, so these two ports are separated by lambda g by 4, and these two ports are again separated by lambda g by 4. Okay, all these ports are separated by lambda g by 4. Okay, adjacent ports with each other. Again, this is a lambda g by 4. So when these two signal comes over here, this has traveled a total distance of lambda g by 2. This again has traveled a distance of lambda g by 2 in this way. But here the polarity is different. So when the same signal comes over here with the equal magnitude, they tend to cancel at port number 3, because both have traveled lambda g by 2 total distance. Now here also it is a lambda g by 2 over here, right? So lambda g by 2, lambda g by 2, but with opposite polarity, hence the total signal is going to cancel when it arrives at port number 3, and at port number 3 you will get a 0 output. Okay, so the perfect cancellation will take place in ideal hybrid ring at the designated frequency. Okay, so this hybrid ring or rat race junction can be used by as a replacement to the magic T. Okay, so the magic T and the hybrid ring or the rat race, they can be used interchangeably in the same application. So how simply we can write the scattering matrix if this particular circuit is going to exhibit this property or phenomena? Again, it is a 4-port device. The scattering matrix is a 4 by 4 order, and directly we can write all these ports, port number 1 to port number 4, are perfectly matched to the junction. Therefore, their scattering values of the respective reflection coefficients are 0. So here original matrix is S11, S12, S13 and S14. Similarly S21, S22, S23 and S24, S31, S32, S33, S34 and S41, S42, S43 and S44, right? So this is general matrix. Okay, what we assume, all ports, that is port number 1, port number 2, port number 3 and port number 3, 4 are perfectly matched. As they are perfectly matched, there are no going to be any reflection. So what we can write the scattering matrix then, which parameters we should make it 0 if there is no reflection. S11, S22, S33 and S44 are going to be 0, right? So if you replace these values over here, 0 from 1 to 2, yes. Okay, see here, if this is the hybrid ring, port 1, port 2, port 3 and port 4. Okay, when it comes at port number 1, adjacent port you will get. So from 1 to 2 is possible and from 1 to 4 is possible. Okay, so 1 to 2 is possible, 1 to 3 is not possible, so that's why S13 is 0. 1 to 4 is possible, so that's why you can write 1 to 4. Okay, so similarly S21 from 1 to 2 is possible, right? S22 is already 0, right? From 3 to 2, yes, it is possible, S23, because it is adjacent. Okay, so S24, 2 to 4 is not possible, so make it 0. Okay, similarly S31, so S31 means 1 to 3, 1 to 3 is not possible, it is 0. 2 to 3, yes, possible, S32, S33 is already 0, and 4 to 3 is possible again, that is S34. Okay, you need to read opposite, please remember, from the second suffix to first suffix. Similarly 1 to 4, yes, it is possible, so S41 is non-zero. S42, that means from 2 to 4 not available, you can write it 0. S43, from 3 to 4 it is possible, you can write S43, and similarly S44 is equal to 0. So this is a simple matrix of a hybrid ring or a rat race junction. So the hybrid ring and rat race junction, when at the same, it can be interchangeably used along with the magic T. So whatever application we build using the magic T, the same application can be designed and developed using this hybrid T. Only the difference between the hybrid ring and the magic T is, the magic T is a little bit bulky in the construction, and it does require internal matching when it is not required in the case of a hybrid ring. Okay, so internal matching is required in the case of hybrid magic T, while this case is not required in the case of hybrid ring. So this is the one of the advantage that the hybrid ring is going to offer to us over the magic T. Functionality wise, the working operation of magic T is same as that of the hybrid ring. Only the thing is, the magic T is bulky and it does require internal matching, while this hybrid ring is compact in the structure, in the construction, and it doesn't require internal matching operation. Okay, so I hope that we started with the 3-port devices, and then we saw the two different 3-port devices, E plane T and H plane T, and then later on we combined them together and we saw the working of magic T or the hybrid junction we say, and finally the alternative to the magic T, a simplified model, okay, we saw, that is a hybrid ring. Okay, so with this lecture we will stop over here. The remaining other passive type of waveguide based devices, the important thing is a directional coupler, then the introduction to the ferrite device, in which we are going to see the typical example of circulator and isolator, and finally the gyrator operation and the power divider operation. Then the more or less the module number 2 will get over. So what we do is, in our next lecture we will study the remaining types of passive waveguide based devices, and again in those devices we are going to formulate scattering matrix for some of the devices. Okay, thank you very much.